Hello, Mr. Sorrentino here again, going into section 1.4 lecture notes, which deals with equations of lines and modeling, which is kind of misleading because we've already looked at one equation for lines, and that was slope-intercept form. This one's going to focus on another format, which you can see here is point-slope form, and we're also going to talk about linear regression to a certain degree. Although a lot of the things that they're asking you to be responsible for is calculator driven. I'm going to demonstrate some things on the calculator, but I'm also going to talk about, some things they may ask you to do in a similar manner to, come up with the equation of lines to predict, things based off of data. Um, so the first thing, focus our attention on the point slope form of an equation. Like slope-intercept, this does give us, you know, all the information we would need to draw a line, a point that the line passes through, as well as the slope. These three things here will tend to be numbers. Those minus signs are part of the structure, but they may change to plus signs if I should be subtracting a negative. Um, the only difference is that this particular format gives us a point on the line. It's not necessarily and probably not going to be a y-intercept. And since there's many different points on the line, you could have several different point slope form equations for the same line. That's one of the confusing parts about it, is that you could have multiple equations for the same line. Um, Also, along with that, there's some sign usage that sometimes confuses some students. So, when you look at example 1 part A, you're asked to draw the equation of that line. It's already in slope-intercept form, so, or to take that back, point-slope form. So it's already pretty straightforward. The only tricky part is, and I'm going to do a quick rewrite of it, is I have to be able to look at this as it's saying y minus 2 on the left equals 1/4 x minus a negative 1. That minus sign right here is part of the overall structure of the definition. And so if that's missing, I have to be able to account for it in some way and recognize the fact that this value here is what we're calling h, or x1 in this case. Some still use the h. And this is the y1. So basically, the point that that this line passes through, that this particular equation is giving us, is negative 1, 2, and it's telling us that the slope is a positive 1/4. So I'm going to plot a point at negative 1, 2, and I'm going to go up 1, right 4, up 1, right 4. I'm going to use the ruler because that would be enough. I could also go down 1, left 4, recognizing that this could be also written as negative 1 over negative 4. But, since I do have a ruler tool on this, I don't have to graph as many of the points. I would say do your best to make it look as sharp as possible, or as straight as possible, but I'm not going to hold anyone particularly accountable for it. I'm just going to draw the line. So there is the line for the equation y minus 2 equals 1/4 x plus 1. The next one is also written in point slope form. There was a couple things I could do about it, though. I mean, one, I could recognize the fact that I could rewrite this as y minus negative 4. Again, this minus sign should be part of the overall structure of the formula. And I could have 2 times x minus 0. I could have also just as easily converted this to y equals 2x minus 4 and have it in slope-intercept form. Because what's going on here is the information I'm given, the point, the x-coordinate is 0, the y-coordinate is negative 4, which happens to be a y-intercept, which is the same thing that, I was going to abbreviate y-int, it's the same thing that the slope-intercept form tells us right here, in that the m is 2, which is the same thing as 2 over 1. So I could plot the point 0, negative 4, go up to right 1, plot a number of points using that. So there are the lines that these produce. Again, I mean, it's a simple method of dealing with it, and it's a method that some people overlook because they don't like using it because of the sign issue and remembering that the minuses should be there, and if you have a plus sign, that means you are subtracting a negative, so the coordinate's negative, and some people forget that a lot, so they tend to avoid this one. But a lot of times the information you're given in a problem relates more to this, and point slope form can be easily converted into slope intercept form, and therefore put on a calculator and things like that. So, um, and we'll look at some more instances of that as we move through this and other examples as we go through this particular chapter. Now, the next thing we're going to look at is discussing parallel versus perpendicular lines. So there's a couple things you need to remember. Parallel lines, which means they never intersect each other, are always going to have the same slope. And it makes sense because if you have a graph and you have one line going this way, well, the other line has to be moving the exact same way if they're never to touch each other. And so, just because they look like they're parallel on a graph, you should confirm that by looking at their slopes and making sure that they are in fact the same slope to show that they're parallel. Sometimes I'll have students that'll tell me a situation like this, just because the two lines don't intersect each other and the amount of space that they have there, they'll tell me that those are parallel because they don't touch each other. Well, I mean, if you kind of look at it, if I would extend these on forever and ever, maybe give myself a little bit more room before I do that. If I would extend these lines forever and ever, in their current directions, I would see that they are getting closer and would eventually intersect. I could also just, find points on those lines, come up with their slopes, and see that they are, in fact, different slopes. The other one that you're often asked to do, and we're not measuring angles or anything like that, which is what in geometry we often do to determine parallelness or lack thereof. Is perpendicular. Now, perpendicular means they intersect and form 90-degree angles, much like a vertical and horizontal line. The main thing we look at is that the two lines are perpendicular. Now, this and this are saying the same thing. If I multiply the two slopes together and get -1, that means that the slope of the two lines are opposite reciprocals. So, that means that, another way of saying it is that, M1 would equal -1 over M2 is another way sometimes to explore, which means that if I compare the two slopes, I could see that there was a flipping around the fraction bar and a change of sign. The only exception we don't use for this is horizontal versus vertical, and that's because this one has a slope of 0. This one has a slope that's undefined, and that's because if you do an opposite reciprocal of this, that'd be a -1 over 0, which of course is undefined. I mean, so, there you have it. I mean, that's just another way of expressing it. So keep in mind that this is the same, but most of the time we look at opposite reciprocals. We look at this formula to determine if they're in fact parallel or perpendicular in this case. Same slope is parallel, opposite reciprocal slopes are perpendicular. So in example 2, you're asked to determine if the two lines are parallel, perpendicular, or neither. And so that requires us to know, I mean, anytime you're asked that question, you're asked to determine, you're going to need to know what the slopes are. Here, the slope is 2/3. Here, the slope is 3/2. These are both written in point slope form, which means I can figure out what the slope is very easily just by looking at the number in front of the parenthesis on the x side of things. They're not the same, so they're not parallel. They're reciprocals, but they're not opposites. So that being the case, they're neither. So remember, you're looking for both things to happen, opposite and reciprocal, not one or the other. The next example, again, this is a little on the easier side because this is in slope, the first one's in slope-intercept form. Put my pen back. I was going to say SI. And this one's in point slope. I'm just going to say PS. So they're both in forms that we can figure out what the slope is pretty easily. This one has a slope equal to 2. This one has a slope equal to 2. So for C, this requires a little bit more work because they're not in any form where you could tell the slope immediately. But take a moment, see if you can determine what the slopes are for these, and then tell me if they're parallel, perpendicular, or neither. Well, these are both in a standard form where the x's and y's are on the same side. I'm just going to convert the slope-intercept form, much as I did in the previous lesson, by simply solving each equation for y. So this one here, I'm going to subtract 4x from both sides, giving me 3y equals negative 4x plus 12. And then I'm going to divide both sides by 3. Making sure I recognize there are parentheses that are supposed to be up here, and since I'm dividing a two-termed expression by 3, that both terms have to get divided by 3. This becomes y equals negative 4/3 x plus 4. And for the other one, I'm going to subtract 3x from both sides. And I get negative 4y equals negative 3x minus 24. I then divide both sides by negative 4. Again, recognizing that there are two terms up here, I do have to distribute that division of negative 4. And over here I'd have y. Negative 3 divided by negative 4 is a positive 3/4. X, negative 24 divided by negative 4 is a plus 6. Now I have enough information to answer the question because here I know that the slope is a negative 4/3. Here I know that the slope is a 3/4. These are opposite reciprocals, and therefore they are perpendicular. So once you're able to determine the slope of any given line, or any two lines, you could then compare them to see if they're parallel, which means they have the same slope and they would never intersect. Perpendicular, which means they have opposite reciprocal slopes and they intersect to form 90-degree angles, or neither, which means they would just intersect and form any other angle but 90 degrees. Please don't automatically think that intersection means being perpendicular. Perpendicular is a very specific instance where they intersect each other, and not just any old time they intersect each other. The next thing you're asked to do is to now write the equation of a line that gives a certain description based off of being parallel or perpendicular to another line. So let's have a look at that. So there's two parts to example 3. They want you to write the equation of a line that passes through 10, negative 3, and in part A is parallel to y equals 2/5 x plus 4. Now, anytime you're writing the equation of a line, there's two things that you need. You need the slope, and you need a point the line passes through. That's how you spell through, but it's abbreviated. So, if you have those two pieces of information, you can write the equation of the line in any format. Um, Obviously, if it's a point that's not a y-intercept, it would end a lot quicker if you used point slope, but point slope could be easily made into slope intercept, and I'm going to demonstrate that as I work through this. As you do this, though, you have to be careful that you don't confuse parts of a line that you're comparing your line to your actual line. So the two pieces of information I'm going to need for my line in this one, I need the slope and I need a point that it passes through. Well, the point it passes through is pretty straightforward because they come out and tell us. It passes through 10, -3. Now, if I go back to the line here, this line here is helping me because I'm comparing my line to this one. And I know it's parallel to this line. And since this is the slope of that line, that means that the slope of my line is also 2/5. So my line has a slope of 2/5 and passes through 10, -3. So what I can do is say, okay, in point slope form, I can simply just write it based off of this information as y minus -3, that's the y coordinate it passes through, equals 2/5 x minus 10. And I could go a step further to simplify and say y plus 3 equals 2/5 times x minus 10. So that's an acceptable answer because it's not asking us to do it in a very specific format. However, if you wanted to put it into a particular format, say you wanted to put it in slope-intercept form, all I have to do is solve this for y and simplify it. And so I could say, if going further with this, y plus 3, distributing the 2/5 up there, I'm going to have 2/5 x minus 4, because 2/5 of 10 is 4. And I would subtract 3 from both sides, so y equals 2/5 x minus 7. So this would also be an acceptable answer, except this is going to be slope-intercept. So either answer is acceptable for this because they're not telling you what format to write it in. This one here just happens to be usually the most used format, so most of the time when you look at answers in the book, unless you're told to write it specifically in point slope form, you're probably going to see it in slope-intercept form more times than often. Part B is really almost the same problem, except instead of being parallel to y equals 2/5 x plus 4, it's now supposed to be perpendicular to that point. So again, knowing this one's slope to be 2/5, when I now look at my line, its slope is going to be a -5/2, so that makes it an opposite reciprocal, and it has a point at that 10, -3 again. And again, with these two pieces of information, as long as I have a slope and a point that the line passes through, I have enough to write the equation of the line in any form. So using the information here, I'm going to have that y minus -3 again, equaling -5/2 x minus 10. And with a little simplifying on the left-hand side, minus a negative becomes a plus. This would be the answer in point slope form. Which, this would be a suitable answer for this because it doesn't tell you what form to write it in. However, if If it was a multiple choice item and you didn't see anything written in point slope form, then it might be written in slope intercept, so you would have to go a step further and say, okay, or two steps further, I should say, distribute the negative 5 halves, which would give me a negative 5 halves x plus 25. And then I would subtract 2 from both sides to get y equals negative 5 halves x plus 22. And this would be the slope intercept. So again, either format is acceptable because of the way the question was asked. So, so the thing is always to keep in mind is that no matter what information you're given, if you're asked to write the equation of a line, ultimately you need to be able to determine the slope from the information they're giving you and a point that the line passes through. Sometimes, I mean, they may just say, okay, here's 2 points. What's to write the equation of the line that goes through those 2 points? Well, those two, if you have the coordinates of 2 points, you can figure out the slope, and you have either one of those to use as point slope form, which, you know, if you convert them into slope intercept, they should both convert to the same slope intercept form, although their point slope forms might look a little different. The last example that, well, that we have on here basically deals with linear regression. And it takes up several pages in your notes because there's a lot of calculator usage in it. I'm going to talk about how the problem could be if they don't have you use a calculator, but I'm going to focus a lot on the calculator usage. So let's have a look at that problem. Prescription drug sales. The following graph illustrates the retail sales of prescription drugs for certain years. Model the data with a linear function. Estimate the total sales for 2006 and predict the total sales for 2011. Answers may vary depending on the data points used. Ultimately, that's one of the things that I don't really like about it. It's hard to check your work if they say the answers may vary depending on what points you used. And I'm going to explain what they mean by that momentarily. However, you know, the information you have here, you know, in 2000, prescription drug sales was in billions of dollars, it's $146 billion. In 2001, it's $164 billion, so forth and so on. You know, and essentially, you know, what I first did is we put into this graph here, this table to represent the same thing. Okay. And oftentimes you will see, I'm leaving the year in as the X value. You could also just say, since it started with 2000, this is 0, therefore this would be 1, 2, 3, 4. It makes the numbers a little less fraction involved, or, you know, the decimals are not quite as severe. But, you know, ultimately you have to make sure that you're being consistent along the way. You know, so if you're letting X be the actual year, when you eventually have to calculate your predictions, you have to also make sure that's the case. If you made an alteration to have, like, you know, the year 2000 be 0, everything else has to be accounted for in the same way, or you're going to have some values that are going to be quite a bit off. Now, the thing is, if you were plotting these points, you would see they're not exactly linear. They don't line up as a straight line. They're pretty close, and I'm going to show that eventually when I do a scatter plot. You'll see what I'm talking about. However, they're not linear, because if I, you know, kind of go back to something we had done in the previous chapter. Each one of these are going up by 1. Whereas this one goes up by 18. This one goes up by 19. This one goes up by 20. This one goes up by 18. And so when you're looking at the grand scheme of things, and if you're looking at a graph that's scaled a certain way, these slopes are not going to be vastly different. That's why they look almost linear, but they're not quite linear. This is not a purely linear relationship because of the fact that there are different slope measurements as I move from point to point. As I move from X to X, them being consistent, my Y's are not moving consistently in the same way. So this is not linear, you know, but it's close. So now what they would ask you to do is, you know, pick 2 of these points and then write the equation of a line. And that's where you would have different answers coming from, because if I said, say I chose to use these 2 points. Now I've already determined what the slope was. It's, I mean, based off of just me jumping, the slope, if I use those 2 points, 2001, 164, and 2002, 183. I already got the slope to be 19, which is in billions of dollars per year. My equation, I would say now I have to choose one of these points. I'm just going to choose that one. I mean, so the equation I would have would look a little different depending on which one I use in point slope. But I would say, okay, y minus 164 equals 19 times x minus 2001. And, simplifying this, 19 times negative 19 times a negative 2001 is a negative 38019. And if I add 64 to both sides, or 164 to both sides, I get 19x minus 37,855. And that would be an equation that I could come up with this. The problem is if I had used two other points, I'd have a different slope, which would also contradict and possibly change the b value I would get in this slope-intercept form. So there could be different equations I could come up with, all being very close to each other. If I would graph them, I would see they're not that far off from each other. They're almost, the exact same line, but I could tell that there are some slight deviations that keeps them from being the same line. So that's why there could be a deviation of answers. The best way of determining the best line to use is to use the line of best fit. Now, all this calculator stuff that you see over here, I'm not going to go through it. I'm going to show it. I'm going to demonstrate it as I go through it. But it's all written for you so you could retrace it and things of that nature. So I'm going to demonstrate this on my little calculator here. Let me pull it up. And of course this as well. So you can see everything. Turn this on. The first thing I want to do is I want to get this data into my calculator. This is a statistical regression. So, so I'm going to use statistics, which, and I always make sure to kind of explain that because this is why I know to hit the stat button. I have edit, which lets me edit a list of data, which is what this is going to be. There's calculations I could do, like one variable statistics. Notice that linreg, which stands for linear regression, is there. There's tests you can do too, but that's more if you take a statistics course. So I'm going to edit my data, and I'm just going to put the data in, 2000. So this first one's going to be my years. And I'm going to come over here and put the sales in billions of dollars. Now remember, each one of these represents billions of dollars. I have to be aware of that because when I answer questions later, I have to make sure that if I'm finding out some sort of dollar amount from this, that dollar amount I'm coming up with is going to be in billions of dollars. So there's my data. The first thing I could do is I can actually plot a scatter plot. And so what I can do with that is I can come over to I'm going to do a statistical plot, so this is stat plot. So I'm going to hit second and my y equals at this point. And I can see what kind of plot is on and off. It'll let you do up to 3 different plots. I wouldn't really want to do more than that. So I'm going to turn this one on, and I'm just going to make sure I have it highlighted. Just hit enter. It's going to be turned. I can turn it on. This is for a scatter plot, so I'm going to leave that. I have different choices. X list and I mean my X and Y lists are L1 and L2 by default, and that's what I actually had them in for. So I don't have to change anything with that. I can come down here to the marks. I can change them to, those blocks, plus signs, a slightly filled in block, a much smaller one. I tend to make them a little on the bigger side, leave them here. In this one here, I can actually change colors if I want to. Not a big deal one way or the other. I could, I have a number of colors I could change it to. None of them in particular, are very important, but I now have this information. And so if I hit enter and or quit out of here, I have it turned on. If I hit the graph, I may not see anything, so I'm going to hit zoom and I'm going to choose 9 for zoom stat. And I can see here that, this is the plot of my data. Um, it adjusted my X and Y axis so I could see all the data here. So you don't see much of an axis here because of the fact that it's pretty high up. Um, if I looked at a window here, it's starting at 19996, and the max is at 2004. So it's the X minimum is not even negative. The same thing with the Y min, it's not negative either. So um, you could change that if you want to see a better idea what the graph looks like. But for the sake of our purposes, this is my scatter plot. And as you can see, it does line up pretty well. And if I would come here, for instance, and put in my formula I had down here, that 19x minus 37855, and since it's in blue already, I don't want to make it blue, so I'm going to and if I graph it, it fits this pretty well. Okay, so I mean, I'm not off too much with mine. However, I want to find the actual linear regression equation. So now, going back to, I'm going to quit out of here. Going back to stats again, I could go back to calc for calculate, and I'm going to choose choice number 4. The X list is L1, Y list is L2, no big difference there. I can choose to store the regression equation. You can just leave that alone and eventually just use the regression equation command. Depending on your calculator model, this may not be available here, so you might have to just um, you know deal with that at a later time. But I could now say go to variables and choose Y2 to store it there, and I can calculate it. And what it does is two things. One, it gives me the equation of the linear regression. So the equation that is for the line of best fit is y equals a, which is 18.9, plus x plus b, which is negative 37654.4. So I'm going to write that as the linear regression equation here. Which would be the line that fits the best with statistical analysis. Y equals 18.9x minus 37654.4. Again, not very much different. I mean, 18.9, not a big difference. You might say, well, 37855 and negative 37654.4, that's much more substantial difference. Not so much when you're dealing with billions to deal with. I mean, 376. What's this like? This is yeah, 37,654 billions of dollars. And this is 37,855 billions of dollars. I mean, comparatively, they're not that far apart from each other. So, but one of the cool things about doing it the way I had, going back to this, is if I go back to y equals now, you're going to see that that regression equation has been stored there. My other option, just to kind of show it, is that I also could have just came here, went to variables, went under statistics, 5, and under equations, the very first one says regression equation, and they would have popped up the same thing anyway. So, didn't need it there. So, but I know now that y2 has, the actual formula in there. So, I could use y1 or y2 depending on the case may be. Actually, I would prefer to use y2. Also, getting back to what was produced when I did that. Here we go. These R values. This R value is also a strength of the correlation between them. This 0.999846 means that my scatter plot, those points are pretty close to being linear in the grand scheme of things. If the R and R squared are not following up for you, what you need to make sure to do is go to second, hit the 0 for your catalog. You want to get under D's, so on the matrix you see the letter D here. That gets me into my D commands, and I want to go to diagnostics. It might take a little bit of scrolling, depending on your calculator. And you want to make sure the diagnostics are turned on for this to work. And it should make those R's show up if they weren't showing up before. But the closer to 1 or negative 1 this R value is, the higher the correlation is, the closer they are related to each other. The closer to 0 that R value gets, the less of a relationship there is. So that's kind of a measure, and that's also mentioned in your notes as well. So this indicates to me that we have this equation, this linear regression equation. It's a pretty strong correlation with that. So that means that this would be, if the data is thought to be considered to go on in this manner, it should be pretty, close in prediction values, for anything I predict beyond this. So with this information now, I can now answer the questions we're actually asked. We're asked to estimate the total sales for 2006 and estimate the total sales for 2011. Just to make this short and again, get to the end of this video, I'm just going to, basically that means you're just going to go to either this function you created or this function here that's from a linear regression. This one, of course, is better. That's the one I'm going to go with. And I'm going to basically plug these in for x's, because remember my x's were my years. So if I pull up this again, and go to variables, and go to y2, I just put in the year 2006, so I get 259. So that means that the total sales, the estimated total sales for 2006 would be $259 billion. I have to make sure I am putting the right variables in. It's dollars, and it's in billions of dollars. And likewise, I can do the same thing, except now put in the 11. And I get 353.5 billion. And that's in billions of dollars again. Granted, I could have also used the first one I came up with, because it's not that far off again. I would notice some difference in these values. There's going to be some difference, because if I choose to do y1 instead, and I do 2006, it's 259. So you can see that part's not very far off. And if I do 2011, that one's not very far off. It's off by zero point 0.5 billion. So as you can see, I shouldn't expect to have major differences between if it's close to being linear as it is, a line of best fit that I come up with by picking my own points, or the line of best fit that is made by the calculator by finding the one that fits all the points the best they can. That's how you do it by hand as well as on the calculator. Be sure to read through the comments and such, and make sure you look through over those notes, practice this on your own calculator to get the hang of it, so you can do some more problems with it. If you have any questions, please make sure to reach out to me. Until next time, have a good day.